Today we are going to start with the types of semiconductors. Before going to start with the types of semiconductors, we shall cover some part that we have already covered last week, that is with regard to the classification of solids. We have seen that solids can be conveniently classified into three classes. First is a conductor, second is an insulator, that what we call as a non-conductor, and third is a semiconductor. The points of difference between these three types we have studied is that in conductors, the valence band and the conduction band, that is VB and CB, are very closely spaced because there is a no gap between the valence band, what we call as a filled band, and the conduction band, that is a vacant band or empty band. There is a no gap in between these two bands, and hence the electrons can easily jump from valence band to conduction band, that is from filled band to empty band, and because of which current conduction is carried out. Second, we have seen in insulators or in non-conductors where there is a large energy gap between the filled valence band and the empty conduction band. Because there is a large energy gap, what we call as a forbidden band or forbidden gap, which we call as FB, there is a large energy gap between the valence band and the conduction band, and because of which the current conduction cannot be carried out. So the large gap between the VB and CB that ensures that such materials are non-conductors or they act as insulators. Thirdly, we have seen the semiconductors, where again there are two bands exist. One is a valence band, which is a filled band, and another that is a high energy band, that is a conduction band, which is empty or vacant band. The point to note here in semiconductors is that the forbidden energy gap or forbidden band between VB and CB is very, very small. Because there is a very small energy gap between valence band and the conduction band, the electrons from the valence band can easily jump to the conduction band, that is an empty band, and hence current conduction or heat is carried from one to another end. So these are the three materials which are distinguished strictly depending upon the presence of the gap between the valence band and the conduction band. So one should remember that there no gap exists in conductors. Valence band and conduction band are closely spaced. In insulators on non-conductors, there is a large energy band that is known as a forbidden energy band or forbidden energy gap, which we call as a FB. Large energy gap is there between VB and CB. And thirdly, in semiconducting materials, there is a very small forbidden band exists between the valence band and the conduction band, and because of which the current conduction is carried out. So based on this primary idea, today we are going to study the types of semiconductors. We have seen in semiconducting materials, the forbidden band or forbidden energy gap is very, very small. So these semiconducting materials or semiconductors are classified into two main classes. The first class, that is known as intrinsic semiconductors, and second category, that is known as extrinsic semiconductors. Under extrinsic type of semiconductors, there are again two different types. One is an N-type semiconductor or N-type extrinsic semiconductor, and second is known as a P-type semiconductor or P-type extrinsic semiconductors. The point of difference between these two types, that is intrinsic and extrinsic type of semiconductors, is that intrinsic semiconductors, in which the semiconducting property arises in pure state. There no exist impurity. And because these are, the current conduction is done in pure condition, and hence all such materials are known as the intrinsic type of semiconductors, where current conduction is carried only in presence of the pure materials such as silicon or germanium. But in extrinsic type of semiconductors, we have to add a impurity element from outside to the pure silicon or germanium crystal, because an element or impurity is added from outside to pure silicon or germanium crystal, and hence these pure silicon or germanium crystals, they become impure, and the material that is added from outside, that is known as a doped impurity or dopant. So depending upon the type of impurity or depending upon the type of dopant, whether it is a pentavalent impurity or trivalent impurity, there can be a n type or p type of semiconductors. So initially, in the beginning, we are going to start with the intrinsic type of semiconductors, which are known as a pure semiconductors, and extrinsic type of semiconductors are referred as impure or defect or extrinsic type of semiconductors. So just see how the intrinsic type of semiconductors, they work here under the types of semiconductors. As we have seen that there are two different types of semiconductors. The first type is known as the intrinsic semiconductors, and second is known as the extrinsic semiconductors. Intrinsic semiconductors are also known as the pure semiconductors, and extrinsic type of semiconductors are known as the impure semiconductors, which are also known as the defect semiconductors, which are again of two types, the n type semiconductors and the p type semiconductors. Now we are going to study these two types after some time, before which we are going to study the intrinsic type of semiconductors. We know that pure silicon or germanium, silicon as we know atom number 14 and germanium atom number 32. Pure silicon or germanium, they are insulators. These are insulators, that means they do not carry any current. So at low temperature, these pure crystals, they act as insulators, or what we call as non-conductors of heat and electricity. But as the temperature increased, as the temperature is increased on both this, either silicon or germanium, then the electrons which are present in pure silicon or germanium crystal, the electrons can easily jump or they move from one position to another position, and hence they carry current, and hence they behave as the semiconducting materials or semiconductors. Now the crystal of this, if we want to show, for example, we are going to consider silicon. Silicon having atom number 14, the valence shell electronic configuration is 3s2 and 3p2. If we want to show in terms of a box diagram, then one can show this as like this. This is 3s and this is 3p. 3s orbital containing 2 electrons, while 3p containing again 2 electrons. During the formation of bond between the silicon crystal, one of the electron that is unpaired and it is promoted to 3p level. So the excited state electronic configuration can be shown as like this. This is 3s, 3px, 3py and 3pz, and this we call as the sp3 hybridization of silicon. 1 3s and 3p orbitals, they undergo sp3 hybridization. So as we know, whenever there is a sp3 hybridization, the geometry must be tetrahedral. So here the tetrahedral geometry can be shown as like this, which is surrounded, this silicon is surrounded by 4 silicon atoms like this. This is known as a tetrahedral geometry. This silicon that undergoes sp3 hybridization, or every silicon atom is surrounded by 4 silicon atoms of the same element. Or this particular situation, if we want to show, then we can show this is as like this. These are the silicon atoms which can be shown. This is a crystal structure of silicon which can be shown as like this. This is a part of this crystal structure. Here it is seen that each silicon, as it is a tetrahedral, that means it is surrounded by 4 surrounding silicon atoms, and hence suppose for example if we consider this silicon atom, then it is surrounded by the first, the second, the third, and this is the fourth. So these are the 4 silicon atoms which are surrounded by this central place silicon atom, and this silicon can form 4 bonds with the surrounding silicon atoms by using the valence electrons of 3s and 3p. So there are 4 valence electrons in the valence shell. Now, if we want to show the diagrammatic representation for this, then we can also show the formation of this bond between the silicon atoms like this also. This is a central place silicon atom, and these are the surrounding silicon atoms which can be shown as like this. Every silicon contributes 4 electrons like this. So here the formation of covalent bond between the silicon atoms can be shown like this. This is a central place silicon atom which has undergone sp3 hybridization. So this silicon contributes its single electron, and the silicon atom which is surrounded by this silicon atom, that silicon also contributes its 3s electron. So these 2 electrons share a common pair of electron, and they can form a bond between these 2 silicon atoms. So I have shown the formation of bond between this silicon and this silicon, which is shown here, or this is a, and it can be shown as like this Si, silicon plus 4, silicon plus 4, and silicon plus 4. Again, the 3px electron of central place silicon and 3px electron of the second silicon, they also share their common pair of electrons, and they can form the second bond between the silicon. So these 2 bonds I have shown. Then the 3py electron of central place silicon and 3py electron of the surrounding silicon, they contribute or they share a common pair of electron, and they can form the third bond between silicon, which is shown here. Then the 3pz electron of central place silicon and the 3pz electron of the surrounding silicon, they also share a common pair of electron, and they can form the bond between this silicon. So here in the formation of this bond or this or other bonds, every bond involves 2 electrons. So every silicon is surrounded by 8 electrons, what we call as octet of electron. Octet means again the completely saturated electronic subshell, on account of which such materials are very stable, because the 8 electrons are surrounded by every silicon atom, and hence such material is stable. No valence electrons are available to move inside the crystal, and hence in pure condition or in at 0 degree centigrade, these materials, either silicon or germanium, they act as the non-conductors of electricity. So, because all the valence electrons are engaged in the formation of normal covalent bonds with every silicon. So, this silicon also forms the 4 bond. This silicon also forms the 4 bonds. So, every silicon can form the 4 bonds with the surrounding silicon atoms. So, every silicon is having 8 electrons completely saturated outermost electronic subshell. No valence electrons or no free electrons are available, because all the electrons are engaged in forming normal bonds with the surrounding silicon atoms, and hence they do not conduct electricity. So at 0 degree centigrade, the electrons remain as it is. So whatever electrons are contributed by both the silicon atoms, they are confined or they are tightly bound in the successive covalent bonds. So, because no movement of electron takes place, and hence such material, they act as a non-conducting material, or what we call as a non-conductors or the insulators. But if we increase the temperature, if we increase the temperature of the pure silicon or germanium crystal, then because of increased temperature, the bond between this silicon or this silicon, or the bond between this silicon or this silicon, this bond, either of this bond, that breaks down, the bond between the successively silicons atoms, that breaks down. So because of breaking of the bond, say for example, this electron moves inside the crystal, and this can create a vacancy that we call as a hole. So this electron now moves inside the crystal. Now, on application of an electric current or an application of electrical potential, say for example, this is a positive pole and this is a negative pole. So, as electrons are negatively charged particles, they move towards a positive terminal, and holes are regarded as a positive particles and they move towards the negative terminal. So, exact reverse movement of these electron and positive hole takes place. So, on increasing the temperature, the bond between the silicon atoms, that is a covalent bond, that ruptures or that bond breaks up. Because of breaking of bond, one of the electron leaves its space and it moves inside the crystal, and now this electron is regarded as a free electron. And as we know, whenever there are free electrons are there, they can carry either heat or electricity. So as electrons are negatively charged particles, they move towards a positive terminal, and the vacancy that is created by the movement of electron from this side creates an empty space, what we call as a hole, and this hole is regarded as a positive part and it moves to the negative terminal. So now, because they increase the temperature, some nearby electron, say for example, either this electron or this electron, that moves, that leaves its original position, and that now moves to this hole, and this electron now occupies this empty space, which indirectly creates another hole or another electron vacancy. So the process continues, and again this electron now moves to occupy this hole, which again creates a empty space or hole. So by jumping off the electrons, new electron vacancies are created. In order to occupy these vacancies, some nearby electron that, or some nearby bond that breaks, and the electron from which that moves to this hole and occupies this hole, which creates again a new electron vacancy. So because of the movement of electrons and the holes in the opposite direction, the current conduction is carried out, but only in increased temperature conditions. So because the temperature is increased, one of this bond that breaks down or one of the bond that disrupted, and because of disruption or because of breaking of either of this bond, the electrons now are moving inside the crystal, or the electrons are now free electrons, and under the influence of electrical potential, these free electron can move, and while moving they can carry the current. So in doing so, some nearby electrons they also occupy this electron vacancy, which creates a new electron vacancy, and thus the current conduction is carried out. So this is how. Here, one point of difference that I would like to tell you, that at 0 degree centigrade, this pure silicon or germanium crystal that behaves as a non-conductor of electricity, because all the electrons are engaged in forming normal bonds with the surrounding silicon atoms, and hence the condition of electron 8 electrons, that is octet, that is completed. And because every silicon is having a saturated electronic subshell, that is 8 electrons are there, it is as good as the inert gas elements which is having also the 8 electrons. And because no valence electrons are there, and hence such materials are non-conductors or insulators at a 0 degree centigrade. But as the temperature increased, due to increase in temperature, the strong covalent bonds between successively silicon atoms that breaks down, and one of the electron that moves inside the vicinity of the crystal lattice of either silicon or germanium. Or if we want to show the same situation with the help of germanium, then germanium is also a tetravalent, so it is also surrounded by 4 germanium atoms like this. This is germanium, this is also germanium, atomic number 32. Every germanium can contribute its single electron, and the surrounding germanium atom that also contributes its single electron, and hence every successive germanium that can contribute 2 electrons each, hence again 8 electrons are there with every germanium atom, and hence they do not carry any current. But at increased temperatures, the bond between successive silicon or germanium crystal that breaks down, and because of breaking of the bond, the electrons are now set free, or the electrons are quite mobile, or they are movable. And as the electrons are movable under the influence of electric potential, they move towards the opposite pole, that is a positively charged pole. And the electron, when it moves, it leaves its original site, and that creates a empty space of electrons. In order to occupy this empty space of electron, some nearby bond that breaks also, and the electron from this bond, one electron from this bond that occupies this empty hole, which creates a new empty electron vacancy, and this process continues until the current conduction that carried. So here, as the current conduction is carried out only by either silicon or germanium, only in pure state, no impurity that is present inside the crystal structure, and hence the current conduction is carried out by the silicon or germanium crystal, and hence such conductivity is known as the intrinsic type of semiconductivity. So this semiconductivity can also be explained by using the band theory of metals that we have already studied. That in band theory, according to band theory of metals, as we know, that whenever we use the word semiconductor, so at increased temperature, these materials, they behave as the semiconducting materials. But at 0 degree centigrade, they act as the insulators. So at increased temperature, pure silicon or germanium crystal, they behave as the semiconductor. And according to band theory of metals, we have seen that according to this theory, there exist two bands. One band that is completely filled is known as the valence band, what we call as a VB, and another band that is known as the conduction band, which is at the top of this. This conduction band is empty, or this conduction band is vacant, while the valence band is completely filled with electrons. One drastic feature to explain this intrinsic type of semiconductor, that whenever we use the word semiconductor, then we have to mention about the forbidden band. So this forbidden band, what we call as a FB, this forbidden band, or the energy gap between the valence band and the conduction band, this band is very very small. On account of small energy gap between the valence band and the conduction band, by increasing the temperature, whatever electrons are there in the valence band, those electrons can easily jump from the valence band to conduction band. And for jumping of such electrons, very less amount of energy that is required. That means if we just increase the temperature of this pure silicon or germanium crystal, this is either in case of silicon or germanium, in at 0 degree centigrade or at room temperature, they act as a non-conductor or insulators. But on increasing the temperature, because of small energy gap between valence band and the conduction band, these electrons can easily move from the valence band to conduction band, and hence in doing so they can carry the current. So this is the explanation strictly according to the band theory of metals. So sometimes a long question may be asked that discuss the intrinsic type of semiconductivity as in case of silicon or germanium based on the band theory of metals. So band theory tells us that there exist two types of bands, that is, one is a conduction band, another is a valence band. Conduction band is empty or vacant, and valence band is completely filled with electrons. So when increased temperatures, the electrons can easily move from the filled valence band to empty conduction band, and in doing so, they carry the current. So this is how the current conduction is carried out in pure silicon or germanium crystal. So few points you should remember while giving the explanation for intrinsic type of semiconductors, which are also referred as the pure type of semiconductors. In all these materials, the pure silicon or germanium crystal, they do not have any free electrons, because pure silicon or germanium metal or materials, they do not have any free electrons, because there is absence of free electrons, as all the four valence electrons are engaged in forming the normal bonds with the surrounding silicon atoms, and because all the valence electrons are engaged in forming the normal covalent bonds with the surrounding silicon atoms, and hence no free electrons are there or no mobile electrons are there, and hence such materials are non-conductors or insulators. But at increased temperatures, the bond between successive silicon, one of the bond that gets broken, and one of the electron that moves in the vicinity of the crystal. So under the influence of electrical potential, this electron moves to the positive pole, and the hole thus created by the migration of electron, this hole occupied by some nearby bond that also breaks down, and the electron from this bond that occupies this empty space. I am having one video I will show you after the completion of this lecture, and that will enable you for the clear understanding of the semiconducting property in case of intrinsic type of semiconductors. So you have to again join by clicking the same link, because we are having today again two seminars. So I'm going to conclude this meeting